All right. So what we left off from last week was that hey, we have logs, right? And we kind of have the situation that I said, hey, let's say you want to use the bathroom, right? And to do whatever business you want to do, you lock the door, right? But let's say that's a shared resource, which is the toilet paper in the bathroom that's empty. What are you gonna do? Because in that case, you have a deadlock, right? Someone can come in and refill the toilet paper, but you're not going to allow them to come into the room, right? So what can you do? And then we'll move on to the other also really interesting and important topic, which is scheduling. Especially now that your CPU has so many cores available, so much memory available, why would you care about scheduling? So the first thing, let's cover deadlock, right? And to do that, let's develop some theoretical definition. So system consists of resources. I'll denote by the letter R. This can be the CPU core cycle. When I use the CPU core cycle, it means I'll take one CPU and I will run for n cycles. I can use the memory space. I can use the IO device and more. I can use the bandwidth. I can try to occupy the software managed cache. I can occupy the network is also a part of the IO, right? So these are the shared resources. Why do we call them shared? Yeah, first of all, every program, I can write a program to use them, which means that there will be a demand from a program, right? From the user even. And each resource has type R that has WI instances. WI instances, which basically means that I can spawn a bunch of instances that would be given to the program, right? And the process when you're running a program, it utilizes the resource by this order. Request, then I use it, then I release it. Why do we do this? Simplify everything. First of all, I simplify the resource. Everything is just a letter R. Because everything is the same. I want to use a resource. Let me use it. Now I'm done. Release it. All right. Request, use, release. Now here are a bunch of wall of text that say, if you have this, there might be deadlock. If you have this, there might be deadlock. We'll go one by one. All right, one by one. First, mutual exclusion. We kind of covered this already. Basically, it means that I have one process that can use the resource at a time. I have one process that can use the resource at a time. All right. Hold and wait. It means that I'm taking that resource, but I'm also waiting for another resource. It means, okay, first of all, I'm taking RI to myself. I'm taking RI to myself. I'm using the toilet. I'm taking the door lock. I use the toilet to myself. I'm waiting for the tissue paper, which is not here. I'm waiting for the tissue paper, right? No preemption. It means that basically the word preemption means I can stop what am I basically whatever I'm doing to release the resource I have. No preemption is like you are in the bathroom finishing your business. No preemption. You can't stop in the middle and abort. You have to commit. You go and you're done. All right. When you're done, then you release the resource. And the last condition, circular wait. It means that if P1 is waiting for R2, then P2 has R2 but waiting for R3. Then P3 has R3 but it's waiting for R1. So you have this condition where everyone wants the other person's resource in the circle, but that resource is then occupied by that another process. Okay, what do we have here? deadlock, right? The last condition, basically the combination of these four, when you have all these things combined, you are likely, well, not likely to be honest, depending on the order of things, but you might have deadlocks. And the thing about deadlock is, let's say you're running a computer, right? Let's say you're running a computer. If you have a deadlock, what does it mean? Okay, how do you fix a deadlock from the user point of view? I'm running a program, it frees up. It frees up, I cannot do anything. Close the program, which is not nice, right? You lose progress. You have to rerun things, and you have no guarantee you're not having a deadlock again. All right. Let's say you're running a self-driving car and you have a deadlock. You can die. All right. So you better not have that. Okay. So today we'll talk about how to avoid it, how to detect and avoid, or one of the two, right? So the first thing I will talk about is what we call resource allocation graph. As the name suggests, it's a graph. So a graph needs to have a vertex, basically vertices and the edge, right? Vertices is like a node that represents some data. The edge represents the relationship between each vertices. So that's a mathematical definition of a graph. Edge represents some relationship between each node. What's in the node here? So the node can be either the running, well, basically the process in the system, it can be running or it can be stopping. Either one works. But it's a process in the system, and R means the resource. P is the process, R is the resource. The edge can go two ways, directional. You can have a request edge, means that if I do P1 arrow sign RJ, it means P1 want to request RJ. Assignment edge is a direct edge between the resource back to the process. If I have RJ pointing to P1 means that right now resource RJ is taken by P1. It's taken by P1, it's assigned to P1. All right. So there can be multiple type of the vertices, right? Yes. The edge. The vertex is either process or resource, as you can see here. I can have the process I trying to occupy some resource. Yes. The what? When? Okay, sorry about that. So basically, the resource is like CPU, the memory, the IO, basically the resource, the hardware that the process wants to use. Or to be honest, the process can use. Then the process, which is this circle thing, can request the resource, right? For example, I can request the CPU and then request the memory because I need to run. I can also hold the resource, which is the inverse direction of the arrow. Now the resource is occupied by a process. And here's an example, right? Over here, how many processes do I have? 3, right? And then right now I have 4 resource type, R1, R3, R2, and R4. R1, R2, R3, and R4. It can be like one of them will be the CPU, the other one will be the memory, for example. The dot is the instance of the resource that I can issue to each of the process. All right. The arrow over here means that P1 wants R1, which right now is assigned to P2. Again, P1 wants R1, but is assigned, this guy is assigned to P2. P2 wants R3, which is assigned to P3. R2 is assigned to P1 and P2 at the same time. For example, maybe it's a memory, right? Over here, is there a deadlock? Why? R1 wants is demanded by P1, right? But it's not a deadlock. So definition of deadlock is there's no progress. If I keep running my computer, if I'm running my computer, what will finish? P3, because P3 has everything it wants, right? So I'll finish P3. I'll clear up R3, which means that now P2 can go. Because now P2 will occupy R3. The arrow from R3 will now point to P2. P2 doesn't have the outward arrow, means that I can keep running. I have all the resource I want and I can finish. Now when I finish, P1 will get R1. R1 will now point to P1 and then P1 can then finish. All right, so this is okay. What about this? Now everything looks the same except now P3 wants R2 and R2 only have 2 instances. Okay. Now there's deadlock because no one can make progress. P1 is waiting for R1, P2 is waiting for R3, P3 is waiting for R2, which both instances are now occupied by P1 and P2. So I cannot assign R2 to any one of this. So here, as you can see, there's a deadlock. All right, so let's say you are the user and you can, let's say you are the god of this system, right? How are you going to fix this? High level, you don't have to go into the detail, but let's say you run into this scenario. How would you fix this? You can, for example, change the resource, right? So that you have the third instance of R2, which can be shared by P3. Now you're okay. So that's one way. What else? You can kill P1 and P2, right? Well, you can kill either one of them because as long as you have one free, you're good to go. You can kill P1 and then restart P1 afterwards. So that means obviously you have to run P1 at some point in time, right? So you can release R2 from P1, reassign to P3, then rerun P1, right? So these are some of the possible options. The third option is like make sure this thing never happens, right? Limit sharing, right? So you can also have the case where that's a cycle. Obviously, there's a cycle here, right? But it might not be a deadlock as well. Why is this the case? Why is this okay? Well, P3 wants R2, but P2 and also P1 wants R1, right? But if I let this running, what process are gonna keep running to finish? P2 and P4, right? So one of them will finish first, release this guy. Now I can occupy this. This becomes owned by P1, P1 finish, which release R2, right? So in this case, we are fine. What does this mean? If we have a cycle, it doesn't always mean a deadlock, all right? So here are some concrete examples. Remember, we have locks and mutex, all right? So right now, let's say we have 2 mutex. The first mutex and the second mutex. All right. What happened here? So let me label the lines. Let's say this is line number 1, line number 2, line number, like set of lines number 3, 4, and 5, 6, 7, 8, 9, 10. What is the sequence that I can run and I will run into a deadlock? I run line 1 and 6. What happened afterwards? The second line cannot run because the second thread lock the second mutex. Right? So if I run line 1 and 6, both mutex are taken. Both mutex are taken, right? Which means that it's a deadlock. If I do run line 6, then line 1 doesn't matter, deadlock as well, because both mutex will lock each other out. If I run line 1, then line 2, am I okay? Yes, because then line 6 will never happen until I'm done with line 5, which I release. No, until I'm done with line 4, which I release the second mutex. Which also means that if you run this program 1,000 times, what are you gonna see? Somehow it works, somehow it doesn't work. All right, fun. Okay, but here is one example of deadlock, and this happened just based on the order of the instruction that the CPU choose to run. All right. So is the hardware wrong? No, it is basically running what you're telling it to run. Is the compiler at fault? No, it's compiling the code based on the programmer specification. This is basically a software bug, right, that caused a deadlock. To fix it, you have to fix the code. Yes. Okay, here. Imagine if you run line 1 and line 6. What happened? Yeah, both functions are like handled by one other thread. Let's say do work 1 is run by thread 1, do work 2 is run by thread 2. Thread 1 then start line 1, lock the first mutex. Thread 2 comes in, say, hey, I want to lock the second mutex. No one can make progress. All right. So basically that's what happened. And because no one can make progress, I will never reach the line that I unlock things. All right. To fix this, for example, you can kill one thread. All right, but how is the program detecting that? It's not easy. It's impossible. So here are facts. Graph with no cycle always means no deadlock. If no cycle, I'm good. Graph with a cycle, if only one instance per resource type, deadlock. If several instances per resource type, the possibility of deadlock. All right. Stress on the word possibility. Dealing with deadlock. Here are some strategy. All right. High level, I want to make sure I never enter the deadlock state. So you can do deadlock prevention, deadlock avoidance. We're gonna go into the detail. We're gonna go into the detail of each of these strategies. Also, the other thing, I let them run into deadlock, recover by rerun something to make sure that I am now on the state that there's no deadlock. Or I can ignore the problem and pretend deadlock never occurs. This is used by most OS, including Unix. Okay? Assuming the programmer can identify and fix it themselves, not my problem. Okay. All right, so let's go by one by one. Deadlock prevention. Deadlock prevention. To prevent deadlock, one thing we can do is now make a stronger assumption to make sure the way you make requests is different. First, you can enforce mutual exclusion, right? If you have a shareable resource, then shareable resource basically means that this is a resource that I can freely share to everyone. Why are read-only file shareable? Only read request. No one is going to write or modify this, which means that in whatever order, nothing will change. all right? Nothing will change. But if I don't have the non-shareable resources and you want to actually use multiple, like use by multiple threads, have mutual exclusion. Make sure they are used by one thread at a time. The word mutual exclusion basically means that only one entity can use the resource. Hold and wait. You must guarantee that when a process requests a resource, it doesn't hold any other things. It doesn't hold any other things. So one thing you do is, let's say I'm requesting a resource and I allocate. I enforce the condition that if I plan to request anything, I better be able to allocate the resource that I want to me before I run. If I need anything, everything has to be mine before I can run. What's the downside of this? It's not nice, right? It's like dictatorship. If I'm a process, I will allocate and use everything. And then if someone else wants the resource, wait. Okay. You can also perform preemption. Basically, from the condition of no preemption, why can't we preempt? Preempt means that one thing you can do, right? If PI wants the resource RJ, right, RJ, then I do resource preemption. Whatever I am holding, whatever I'm holding right now, I'll release them. Everyone can use it to guarantee that everyone can now make progress. Then I'll build a list and okay, these are the things I want. These are the things I want. Then I restart only when I can regain the resource in the waiting list. This is a little bit more opportunistic. I try to run. Now, if I discover I need RJ and it's locked by someone else, I release all my resources, put in the list, say, hey, I need all this thing. So that the next time I run, I need to make sure I have all this before I can run. Circular wait, well, you can impose total ordering of resource type. Each process will have to make a request to the resource in the increasing order of enumeration, which is not really exactly obvious, like an easy thing to do. Right? You kind of have to mark basically all the requests. Basically, every time I make a request, I need to have an enumerate them, like request 1, 2, 3, 4, 5, 6, 7, 8. Then make sure I have the total ordering of resource. So one common approach is what we call lock ordering. Lock ordering, right? You saw earlier you have two mutex, right? The first mutex and the second mutex, and then the order is like the first thread lock the first one, the second thread first lock the second one, not then the first one. If I have to lock 1 and lock 2. And right now I want to make a transaction from 2 accounts. Basically, the program here, I'm trying to transfer the money from account from into the account 2. I want to transfer the money. What must happen? To make sure that the bank will not run out of business, what must happen? First of all, the whole transfer has to either never complete or finish completely, right? I should not be able to like run into the middle of the code and then stop and then hey, deadlock. So the first thing I need to do, lock both accounts. I need to lock both accounts because I'm transferring the money from both accounts. This one will go down, this one will go up, right? So I need to lock both of them. So I'll say lock 1 equal get lock from, lock 2 equal get lock 2 to make sure lock 1 and lock 2 is now something that I can acquire. Then I acquired lock 1, then lock 2. But look at when I release. I release lock 2, then lock 1. This is what we call lock ordering. When I acquire the lock 1, then 2, I need to release 2, then 1. Because if I release lock 1 before lock 2, it means that someone can come in. When I release lock 1, what happens? So right at this line, let's say this is lock 1, this is lock 2. Lock 1 is from account, right? Someone want to make another transaction. I want to occupy lock 1. So another thread come in. Hey, I want lock 1. Okay, there you go. Another thread come in. Want lock 1. I come in. I actually acquired lock 1. Now I acquired lock 1. I need to acquire what lock next? Lock 2. Can I? Well, Okay, so you release lock 1 first. You cannot acquire lock 2, right? So you wait. Okay, how about this example? So it's okay if the account 2 is another account, but let's say I have account A and B. So the first transfer is from to 2. The second transfer is from 2 back to from. All right, so now what would happen here? All right, let me address this note here. Okay, so I'll use transaction 1, all right, and transaction 2. So the first thing is I acquired log 1 is from, right? Then I acquired 2 followed by release 2, then release form. Over here I acquired 2 So first of all, is this safe? If transaction happen at the same time, what happened? Yeah, right? You have deadlock. So how do we fix this? So yeah, so one thing I can do, first of all, I can make this two atomic, which means that if I require lock, I require everything, right? I can also make sure I order this so that it's always account A and B. Would this okay if I change this way? So will this be okay? So if I take from, I guarantee I have to take 2. Because if I take from, no one else can take 2. No one, like thread 2 cannot randomly come in and take 2. Right? So you try to guarantee the sequence of what should happen, right? So that this crisscrossing of I acquire another lock in another from another thread, which then deadlock the whole thing, never happen. Yeah. So what I want to guarantee here, right, is that if I happen to acquire the first lock, no one else should be able to acquire the second lock, because if they acquire the second lock, I'm doomed. ครับ tx1. So I just want to denote that's the first transaction, the first thread, second thread, right? Notice how here I said get lock, right? Get lock, and the lock itself is a mutex, all right? So I basically enforce that lock one is gonna get the lock from lock two is gonna get the lock from the two account. Yes. Yeah. Yes. Uh-huh. Right. Mm-hmm. Oh, you mean like what if I switch this, right? So in like let's say if the code is more complicated and like after you release lock 2 there's like some more code that deal with mutex, right? Then that can something bad can happen because lock 1 hasn't been released. In this case it's okay because if I release lock 2 I guarantee that lock 2 will be free. Let's say someone wants lock 1, well I'll free it anyway, so that's okay. So in terms of like more complex code and like something is written to release, that means you want this ordering, meaning that if lock 2 is inside, you release lock 2 first, then lock 1. Another thing to note here, the mutex is the lock, not the get lock from, the lock itself. So from here, it's not acquired from and acquired to, it's always acquired lock 1 and acquired lock 2 for both threads. It just happened at lock 1 and lock 2, which like think of it as the actual lock, right? Which I can put it on any door. That door is this get lock function. But the order of how I take the lock will be the same. Always get the red lock, then the blue lock, which then I release the blue, then the red. For every program, for every thread. The order always be lock 1, then lock 2. I decouple the lock and the resource, basically. Now it's the two different things. The lock is the same order. So this becomes lock 1, this becomes lock 2. This transaction is still lock 1, right? This is lock 2, which then the guy can now enforce the lock in the same order for every program. Right. So to answer your question, sorry about this. Transaction, think of it as two threads, thread 1 and thread 2. The problem comes in if thread 1 lock the account itself, lock the account from, the thread 2 lock the account to first. What I want to do is I create the lock, and now the lock is associated whatever account I assign to, but the orders I always lock 1, then lock 2. So now for every single thread, I would need to do lock 1, then lock 2. So let's any question? Any more question? Actually, any more question about this? This I think this should be okay because the order like the lock is now separate from the resource. Yeah. So okay, let me put it this way. Let's say mute. Okay. One thing here is mutex has to be like shared by the two threads, right? Because it's a shared mutex. I better put that like outside, which means I can each one of these threads can call the mutex and lock them. Now, I don't want to directly lock the account from and to, I want to lock the mutex, right? And because the mutex is shared and now it's order, so if I do lock 1, then lock 2. Now every single thread will lock the mutex. So every single thread will do this order, lock 1, then lock 2, which is okay, right? Which is okay. So think about it this way. If I have 2 threads that are concurrently running, and it happened that thread 1 run the first line, acquire lock 1, right? Thread 2 comes in, it will not be able to acquire lock 1 for sure. Because it's the same order, so the first thing it's going to acquire lock 1, okay, it's locked, so I cannot acquire that. The first thread that already have lock 1 will then acquire lock 2, and then finish, release lock 2, then release lock 1. And that's okay. And also it's different from the earlier example where we have the p-thread example, where now the mutex for each thread is in different order. So in the other example that has deadlock, the first thread acquires lock 1, the second thread then acquires lock 2 first, rather than lock 1. So in that case, you have this crisscrossing of like lock acquire, like request to the lock, which will then deadlock. In this case, because you already, like you guarantee the ordering of I need lock 1, then lock 2, then I'm going to release lock 2, then lock 1, you are safe. What's the downside here? Again, for every lock that you have, sequential execution. All right. When you're locking, you have 2 transactions. The transaction 2 has to wait until transaction 1 is done. Okay. All right. Deadlock avoidance. So let me actually talk about one more problem too, right? So let's say when you go to a bank, how often then you're gonna have to, like, how often are you gonna have the transaction that look like this happening in parallel? Almost never. Like, what in the sane mind who would do this, right? So quick question: if you're not locking anything here, like you're gonna get really high throughput, right? Because everyone can, no lock involved, right? Parallel processing. But you have to make sure you do this to make it safe. To make it safe. That's why things like atomic is useful. Atomic, unlike locks, I'm just basically trying to motivate a different alternative. Atomic means I will assume nothing bad happened. I'll keep running. If something bad happened, I will detect, abort 1, then rerun. Why is it going to be useful for this bank test? Because as you said, this is not going to happen. Who in a sane mind would transfer the account in this interlocking manner, right? This weird. So if I'm like most of the implementation in this case, I will use atomic. I'll guarantee that, well, if this thing actually happened by some weird, I don't know why, like sketchy people trying to like launder money or something, I'll detect and only let one transaction go first, then retry the second transaction. Otherwise, I just let them run in parallel, right? Okay. Second strategy, right? Deadlock avoidance. Sorry about this. This is what happened when we're making the slide. Yeah, literally this is what happened. Nothing related to content at all. It's funny. So I took a picture. Nuan, which now I renamed to Inuan. Yeah. Anyway, so yeah, at 4 and 5 o'clock in the morning, my two, like after we cats, 2 of them like will alternate to like use the keyboard, and yeah, this happened. All right, deadlock avoidance. Basically here, I require the system to have some additional a priori. I would murder this word always. A priori information available. I want to know information, right? So if I want to know more information, I need to develop some model, some assumption, basically some assumption, right? that like here basically, if I want to avoid deadlock, I need to know more about the process. What are the resources that the process will need? So I can do all the scheduling I want from the system point of view, right? What's the downside here? First downside. As a programmer, is it annoying? Yeah, you have to label everything, right? So in this case, each process has to declare a maximum number of resources of each type it may need. All right, fun half folks to use Rust before. This is kind of like something that Rust is forcing you to do. You kind of have to declare everything, right? And then you have to declare the ownership. I think I need this. I don't need this. It is read sharing, so I can share them, right? Benefit. Deadlock avoidance, right? Now you can dynamically examine the resource allocation states and make sure there's no circular way, and you're good, right? So the idea is, well, if deadlock is hard to deal with from both the programmer and the system point of view, right? Why don't we try to make sure that I will assume the programmer is capable of declaring what are the things I need. Then from the system point of view, because I control the runtime, right? I control the runtime, I control who gets to go when. I'll do my job. With the additional information the programmer give me, right? Again, system is about software engineering, with software building, right? We can design it this way. So the hope here maybe is simpler, right? And the resource allocation state is basically the number of available and allocated resources. Two things, available and the allocated resource. Allocate means I make a request and it's allocated. And the maximum demand depends on each process because I write a program, it depends on how much I want, right? So here's a safe state. If I have a process number I wants to get the resource number J, the job of the system in this case is to figure out is the allocation safe, right? Is the allocation safe? My bad. Is the allocation safe? Sorry about the typo on this like lowercase thing. But so here, let me assume that right now the system has a bunch of processes running, right? And let's say process I is process number 10. Process number 10. So let's say assume that PI here is 10. What I can do from a system point of view is, if PI need to request these resources, I just need to guarantee that, hey, for all the process before me, P0, P1, P2, P3, P4, P5, P6, P7, P8, P9, I give them all the resources and I still have the resource I can give to P10. P10 is good. It's as simple as that. If there's a sequence of processes from P0 to Pn, and I'm trying to figure out for P10 or P20, can I schedule P20 with the resource demand that the P20 want, right? Anything before me from 0 to 19, they use some resources already. Can I give the remainder to 20? If I can, good. If I cannot, I will wait. Because now I have this ordering of processes, right? If I wait, someone's gonna deallocate that resource, which means that at some point there'll be enough resource for P20, which then P20 can run, then you can figure out what to do for P21 and P22. All right. And let's say in this case P20 is not running, and I have another process P21, which is like the main function do one thing. I want to do A plus B. Then P21 can probably run because it doesn't really need any resource except the CPU, right? So in that case, you can still holding the like P20 because P20 is still demanding some resource that it doesn't have, but P21 now can run. So the OS will say, hey, P21 can run, it's fine. That's okay. Question? Yes.
One can run the P0 to 20 of all the resources. And P21 can run this in the same.
Yes. Basically, the way we figure out the safe state, in this case, be opportunistic, but sort from P0 to Pn. Be opportunistic means that if I have resource to run, I can run. I will just allocate the resource to that process. If I don't have it, I'll wait. And I'll keep doing this for all the process. Yes.
If
you're in this case, yes, because you're gonna wait for the the only time you check, right, is you check if the earlier process occupy the resource I want. And also with this model, the earlier process will run or are running. Or if they are waiting, they're also waiting for even earlier, right? Which means that if they are waiting for even earlier process, they will eventually get to run, which then eventually finish, which will then eventually have the resource I want to run. It's kind of like induction in some sense. If you think about it, like this guarantee P0 definitely will finish, which means that P1 will definitely finish, which then guarantee P2 will finish, which guarantee that any P that hold my resource is gonna finish. Huh?
So this guarantees that.
So you can still do parallel execution, right? Because you only look at, do I have resource to run? If I do, I will run. So let's say I have 10 processes and the first 9 process doesn't really need much. I need 1 CPU and I need like 10 megabytes of memory, right? And I have a system with 4 CPU. It means that I'll first run P0, P1, P2, P3 because I have 4 CPU, right? I'll run 4 processes at the time. It doesn't hold any resource except the CPU, which means once the P0 is done, P4 can then start. Yeah. It only waits for the resource is demanding, basically. It doesn't say, hey, but the thing is, CPU is also a resource. That is also a forcing function. Well, but at the same time, it allows you to run in parallel. Yeah, so basically what I just explained is the in other words stuff. If I'm waiting for the earlier process and I need some resource they occupy, I will wait. But this allows the order of finish, like all the process finish in this order P0 Pn, which means that I guarantee this thing will not deadlock. So if the system is in a safe state, it means there's no deadlock. If it's in an unsafe state, it doesn't always mean deadlock. Just a possibility of deadlock. All right. Avoidance is make sure the system will never enter the unsafe state. That's why we call it deadlock avoidance. I avoid that state by guaranteeing that it's always a safe state. All right. Downsides. Well, first of all, as a programmer, you need to declare what resource are you going to use, right? If you, how many of you write a Python code that is like the interactive version of Python where you type in one line and hit enter? Anyone did that back in the day? Yeah. How can you know what you're going to use in the future? You're not even typing it in yet. The system has no way to know, right? So that's one example. Yeah, how can I know what resource am I going to use for the process? But in that case, it's like run one line, right? And it maintain the process and stop the resource. So it's sometimes it's not as simple to apply this for the whole system, right? But if you can, yeah, it can be useful. So here's avoidance algorithm, right? So if you have only single instance of resource type, which is not realistic, right? It just means like you only have the CPU, for example, or you only have the memory, but you don't have the CPU. Okay. Not sure how that's possible. But then you can use a resource allocation graph. Oh, my bad, my bad. Okay, first I read it wrong. Sorry. Oh, sounds so weird. The first case is like, let's say you only have one CPU and a single instance of memory. No one can share this memory. Like you can't use memory by multiple processes. Then you can use allocation graph. If you have multiple instances of a resource graph, you can use the Banker algorithm. So I recommend you to read this on Wikipedia, look it online, because obviously it's already, yeah, more than halfway through in terms of the time we take today. So I have to go through scheduling, all right? Now for the resource allocation graph, I want to now declare more things. I want to say claim edge as processor PI claim RJ, right? We can use the dash line for this. Then the claim edge will convert to the request edge. Claim is when I declare I want this, but I'm not requesting it yet. Once I make a request, I change to the request edge. Then if I'm doing the request and the resource is allocated to me, it becomes the assignment edge. So there are three types now. I can make a claim saying at some point in the future, I will need this. Request means it's now the time I need this. Assignment means that, okay, this thing is now allocated to me. Three status for the age. When a process release the resource, right, the assignment edge reconvert back to the claim edge. Because I don't need it anymore, so it's not a request edge anymore. Now, the claim must be a periodized in the system. So the algorithm is, suppose I have PI requesting RJ. I can only grant, if I can convert the red to the orange, right? Request into assignment. That doesn't result in a cycle. When I make assignment edge, I don't have a cycle. So here, right? Oops, sorry. Claim, right? It basically means P1 and P2 wants to use R2 at some point. All right. And now P2 request R1, but it's grant to P1. It's grant to P1. Right. So this is okay. I mean, P2 will get R2 because it's making the claim to R2. Finish. My bad. P1 will get R2 eventually. Finish. Then both R1 and R2 will free up. Now assigned to P2. This is a unsafe state. Why? P1 is claiming R2. R2 is now assigned to P2, which wants to request R1, but R1 is now assigned to P1. Why is this unsafe? Because if I convert this, right, to a request, what happens? You get a circle, right? You get a circle, which means it's unsafe. Again, the conversion, because we don't know when that's gonna happen. Right? We don't know when that's gonna happen, but the algorithm will prevent this case from happening. All right. Any question before we move on to the last thing we will talk about regarding deadlock? Okay, so this is actually simple to explain. I'll just let the system go. If I detect deadlock, recover. All right. So that's the two things you have to do. First, it means I need to be able to detect that is a deadlock. Second, If I detect a deadlock, I need to have some scheme to recover. I need to be able to recover from a deadlock. All right. So if you have a single instance of resource type, you can maintain what we call the wait for graph. Again, the node are processes, right? If I have the edge, means the request edge, means I'm waiting for the resource. Then I search the graph. Now I don't make the edge when I'm making the request. I'm making the edge when I'm waiting for the resource. I'm waiting for the resource. Well, we can think of it the same way. I'm making a request on the resource. It's not allocated to me yet. It's not allocated to me yet. Then I write a program to go through my graph and see if there's any cycle. If there's a cycle, it means there exists a deadlock. Now you might be asking, what does it mean for the word wait for? Why am I not using the word request? So here, wait for means that, let's say I'm requiring a lock, I'm actively waiting for that. Right now at runtime, I'm waiting for that resource. And if I'm waiting for something and this is a cycle, it means that there's no way I can get out of this because everyone is waiting for someone else, right? And you can build an algorithm in the order of n square operations where n is the number of vertices, number of vertices, which can be quite big. You can have a lot of process running and you can have a lot of resource, right, available to you. So this can be quite, well, in the system, it's probably in most cases not way too bad. It's not great. Let's say here, right, I have a resource allocation graph. So the left side is what you've seen earlier. Left side is what you've seen earlier. The wait for graph, the arrow is from the process to another process. And right now P1 is waiting for P2. Why? P1 wants R1. R1 is assigned to P2. It means that P1 is waiting for P2. Hey, finish, please, so that you can unlock R1 so that I can use it. All right. P2 is waiting for P5 because P5 is the one that has R3. P5 has R3 and P2 wants R3. So P2 is now waiting for P5. And the same thing, right? So we're done with this and with this. P2 is waiting for P3 because P2 requests R4, but R4 is now allocated to P3. And P3 is using it right now. P3 is waiting for P4. P2 is also waiting for P4. P4 is waiting for P1. Is there a problem here? Is there a cycle here? Is there a cycle here? Yeah, it's actually quite a bunch of cycles, right? So you can keep the system going on. It'll keep running, right? It'll keep running. Then you run the graph algorithm to detect a cycle. If you now detect a cycle, yeah, you have a deadlock. So now we're done with the detection part. If you can get the wait for graph, build the wait for graph, then detect a cycle. If there's a cycle, we have a deadlock. Right? The question then is, I said, I will keep trying out and see if there's a cycle or not, right? So the system question is, how often do I need to run this algorithm? Because I will let it happen, and if there's a deadlock, I will detect it. Which means that if I do it really often, it means I can detect the deadlock really early. If I do it like once every 1 hour, then it means that the first minute, let's say the first minute you have a deadlock, you will not know until 1 hour. If I check every 1 millisecond, it means that for every 1 millisecond, I can detect deadlock. What's the overhead here? Who run the detection algorithm? The CPU, right? It has overhead basically. When I'm running this deadlock detection algorithm, right? it lower my performance if I do it too often. So that's a design decision. So the second thing, if I have a lot of cycles here so the thing is, if I don't run detection algorithm often, right? And let me go back one slide. Here, there's a bunch of cycles. There's a bunch of cycles. You don't know what to kill. Because if you kill one thing and you're gonna get rid of the cycle, it's not clear. Because now it's already multiple cycles. If you only detect one cycle, it means that I just kill anything in that cycle, I'll be good, right? But now it's not clear. Now that's the detection algorithm. The recovery is, well, it's as simple as I kill the process. Hopefully I don't have cycle anymore. One thing I have to do, I abort everything. I want to abort all the deadlock process, right? But if I abort everything, what's the downside? Everything you run is the work you did, right? Let's say you are doing a homework and you have a deadlock. I told you, like, delete everything, redo the whole thing. You'll be killing me, right? So one possible strategy is I'll random, well, not random. I have some mechanisms to pick. Okay, maybe I should abort this and see if there's any deadlock, so I can do this. Now, the strategy would be, what should I abort first, right? What should I abort first? And these are design issue. I can pick any of these choice, and for a combination of this, I can defend my decision. I can defend the decision to include that criteria or not include that criteria. I can look at the priority of the process, how important it is. I can look at how long that process has been running. For example, it's been running for like 99% of the process lifetime. I am almost done, right? I maybe want to keep that guy because it's almost done, right? Some process will occupy, say, 5 gigabytes of your memory, right? If you are running out of memory, maybe one nice target is abort Google Chrome. It actually use a lot of memory, right? So if I use a lot of resource, maybe I want to kill that first. The resource, the process needs to finish. Give me a second. All right. Sorry about that. So how much more resource do I need until I will finish? Because if I have a claim information that say I need this and this and this and this, and this process needs a ton more, maybe kill that guy, because it might be hard to satisfy all those requirements. How many process will be need to be terminated? Because ideally, I want to just terminate one process and I will be good, right? Is the process interactive or batch? For example, if we use some app on the phone right now, and it just happened that my deadlock avoidance, my recovery mechanism will kill the app I'm running right now. I'll be more pissed compared to background apps, right? With background apps, I will not notice that it gets killed. So interactive versus batch is also another important thing. So you want to select the victim that minimize the cost, and the rollback mechanism is, it's like when you play games and you do load and save, right? You might want to roll back to the latest part where you can restart the process. But somehow you cannot tell. So one strategy is to save often, right? To save the state often. The issue with saving the state often also comes with overhead, because every time you save the state, there are like additional CPU and memory that has to be used just to save the state. The another problem is what we call starvation, right? And as the name suggests, right, you have, let's say you have 10 processes, and it just happened that process 10 never get to go. A sad process, never get scheduled because I always get preempt all the time. Every time there's a deadlock, I'm gone. Every time it's deadlock, I'm gone again. Every time, yeah, I never get to run, right? So one strategy is if I get rolled back 10 times, if I get killed like 10 times already, maybe the next time don't kill that guy. To be fair, like basically to increase fairness and prevent starvation. All right. Any question before we go? Let's take a quick. Oh my God. Yeah. Quick question for you guys. Would it be okay if I need to plan this out? I'm not sure I can cover scheduling in 40 minutes. So we'll continue on the next lecture, and we might have to continue and spill over to the network lecture. So we'll use some of those next week for security. I'll prioritize so that the content that will be on the exam are going to be covered on Thursday. Is that okay? So I'll do a like 7 minutes break. We'll resume at 11:30. I'll cover schedule the remaining of scheduling as far as they can go. And then afterward we'll resume on Thursday, and then I'll cover the important part for the basic of the security. And then I'll talk a little bit more about now new problems in security that you can run into. All right. So let's take a quick break. We'll be back at 11:30. Okay, so the next topic is CPU scheduling. And the basic concept, I bought the CPU. I want to use the CPU as much as I can. I want to maximize my utilization. How many people doesn't buy this? Good. I hope everyone buy this. Buy this argument. I have a CPU. I want to maximize utilization. Otherwise, I'll save money and buy cheaper CPU. So here is one of the definition that I'll let you know is this CPU I/O burst cycle. Basically, when you run a program, the OS will kind of usually look at it this way. It's either my program is running using the CPU, or my program needs to use the I/O. My program use the I/O means that it's gonna take a while before I need the CPU again. That becomes the I/O burst. And the CPU burst typically will follow by the I/O burst. Basically, if I use a CPU, want to use a CPU, I will group them together into one single CPU burst, right? And quick note, memory access is a part of the CPU burst. We consider that as a part of the CPU burst. We are gonna deal with that in module number 3 when we go dive deeper into the memory, because that takes a while, but like 100 nanosecond or 50 nanosecond is not as bad as like 100 microseconds. It's about one like 10,000 times worse. So the I/O burst take a while. So that's why we would separate these two out. CPU burst means I need the CPU. When I have the I/O burst, most of the time, I will give up the CPU. I'll handle the I/O, and then I might come back later and resume running. Okay. So here's a concept. For example, my program first initialize something, then open a file and want to read something from a file, right? Originally, CPU burst, when I want to read the file, I/O burst, then I have a content, then do something with the content, then request a file again. So CPU burst, I/O burst, CPU burst, I/O burst. All right. And now here, one of the main concerns is how can I distribute the CPU burst from different programs? So right now, all your computer are running like 10 different programs. Basically running maybe 50 different processes, right? So how do I distribute this CPU burst across all these processes for your running programs? And here's the thing, right? When you look at CPU burst, the plot showed the frequency of occurrence for burst duration in millisecond. What does the plot tell you? Can someone read data on this plot and tell me what's going on? On the x-axis is the burst length basically the burst length. The y-axis is how often does that happen. It basically means that most of the processes, if I have a CPU burst, is basically 1 or 2 milliseconds, followed by some I/O, and then you have like a few that close towards like 8 milliseconds, right, or more, followed by I/O bursts. This trend can change based on like how fast is your I/O. Nowadays it might look a little bit different between your computer, the desktop, and the server, and like your phone. But the key takeaway is CPU burst is usually in the millisecond range, right? Millisecond range. Can someone convert it to me? How many instructions is that? Let's assume a single CPU, and each time, let's assume that each time I run one instruction, it takes 1 nanosecond. 1 million instruction is like one millisecond. I can finish 1 million instructions. Yeah, you're looking at nanosecond, right? So 1 millisecond is a really long time. I finished 1 million instruction already. So this is actually a long time, right? So here's the scheduler overview. These are, but still, millisecond is short term enough. Like, what's your refresh rate on your monitor? 60 hertz. Okay, fancy guy. 144, rich. Okay, so for 144, how often do I have to redraw the image on the monitor? 1 over 144. 1 over 144 in the unit of seconds, right? In the unit of seconds. So this is like basically a few milliseconds. That's why we call it short-term scheduler, because we schedule these things in the millisecond range, right? The user will not notice this at all, and that's okay. It means that everyone will take turn running the CPU, and I'm fine with that. Human will not yet perceive this at all. Human will not perceive this at all, right? But the thing is, the ordering, I can do in whatever I want. Again, now you guys are software developers, right? Which means that, I mean, OS is a software, which means that you can develop the OS. Now let's put that hat on, say, hey, maybe I should control the scheduler and write a program for the OS, right? I write my own scheduler, basically. So the scheduling decision can happen when, first of all, the first scenario is I am running, I switch to waiting, then I need to make a scheduling decision. Who is going to replace the running process? Who is going to replace the running process? If someone switch from running to ready, again, who is going to replace the running process? If I'm switching from waiting to ready, it means that I have a new ready process. Should I change my schedule? Then when I terminate, well, I have one fewer process to think about. Does the schedule change? So I can make this decision based on these things that happen. All right. This assumed non-preemption means that I don't kill the process in the middle of running. All right. So now let's talk about non-preemptive scheduling, because it's simple. You can do the preemption with preemption as well, but for now, let's talk about non-preemption. If I run something, I run until the I/O burst. I finish the whole CPU burst. Okay. You can also schedule things in a preemptive way. For example, I have access to the shared data, right? Access to the shared data. I can preempt one process because they are locking that resource. I can preempt one process to give back the resource that's being shared because maybe you're in a deadlock. If I'm in a kernel mode, right, I can actually preempt while the kernel is running, because the kernel has to yield the CPU back to the user, right? Or when you have interrupts. The dispatcher, as the name suggests, right? Dispatcher is a module in the OS that gives the control of the CPU to the process selected. Basically, I want to run this process. Dispatcher say, okay, go run it on this CPU. All right. This is done by first switching the context. Switching the context means that what all the process, the PCB you seen earlier from last week, save them all, then switch. So the CPU load a new process context. Because CPU has to load, say for example, where's the new program counter, what line should I run, what are the current content of the register file and all those things. Then I switch to user mode. Why do I need that? Well, I need to switch to the user mode to run the user application. Then I jump to the where program counter is pointing, so I can resume that program. Dispatch latency is the time that the dispatcher takes to stop one process and start another. Do you want that to be high or low? Low, low, right? So you want it to be as low as possible, to be honest, because you want to make sure when you make a switch, there's almost no overhead, hopefully. So the criteria for scheduling, this is like getting more open-end, by the way, but you can make your own decision. But here are some goals. I want to keep the CPU busy. I want a lot of throughput, means that I want to be able to finish as many processes per unit of time. I want a good turnaround time, mean that if I execute a process, how long does it take for me to finish that process? Wait time, hopefully that's clear, the time the process are waiting in the queue. Response time, the time when a request was submitted until the first response is produced. Okay, I will compare this to, let's say you want to run a restaurant. Let's say you want to run a restaurant. I want to maximize CPU utilization. I hire a chef. He better be working his ass off all minutes of his life until he, well, yeah. That sounds so wrong on so many levels, but yeah, that's one of the goals. I want to maximize like my chef utilization. Throughput means that if I run a kitchen staff, how many dishes can I cook per hour? But the more I can do, more profit, right? Turnaround time means that if I have a customer, how much time do I have to take to finish serving the customer from the minute he walks in until he walks out of the restaurant? Waiting time means that it's almost like a turnaround time, but it's just the time the customer is waiting. For example, waiting to be seated. Like imagine Momo Paradise, right? You're gonna wait like maybe 2 hours, 1 hour, right? Then you go into the restaurant, the wait time stops when you like order your dish, when you're cooking your dish, and when you're eating. But when you're waiting for your dish to arrive, wait time continues. Basically, anytime the customer has to wait, you go into the wait time. Response time is once the customer ordered their dishes, how much time does it take for the first dish to arrive? All right. And the overall goal is I want to maximize these two things and minimize the other three things. Maximize throughput, maximize utilization, reduce turnaround time, reduce wait time, reduce the response time. Basically, make it as fast as possible and make it as like so that you can finish as many things as possible. So let's try different policy. Give me one simple policy. Yes, thank you. Come next. First come, first serve. After that, I suggest if I come first, I get service first. So let's say I have process A, B, and C, right? And A's burst time is 24 seconds, B's burst time is 3 seconds, and C's burst time is 3 seconds. And the order of arrival is A, then B, then C. So A arrived first, gets service first. The first 24 seconds for A, yay. Then B and C, which arrive maybe 1 millisecond after A, have to wait. So in this case, B resume and then finish by C, 3 more seconds. Wait time for A is 0, wait time for B is 24, wait time for C is 27, average wait time is 17. Is this a good policy? Maybe. Maybe. Can we do better? Probably. Right? I mean, what if you have the different order? B arrived before C, C arrived before A. It's the same policy. First come, first serve, but now A is the last guy. Right? So is wait time better? Yeah, way better, right? So question, this is what we call convoy effect. Convoy effect means that I have a short process that is behind a long process, right? Let's say I have a CPU bound process. CPU, yeah. Which seconds you mean the app? Basically, the burst time of A, if I occupy the CPU and I cannot be preempt, I will take 24 seconds and then I'll go to the IO burst. This number is made up. Usually it's like in millisecond range. But still you see the convoy effects, right? You typically, if you look at IO and CPU, you can classify application that is either CPU bound. CPU bound means that for the most part, I use the CPU all the time. I rarely go to IO. IO bound means that for most of the time, I'll go to the IO. I open a lot of files, and then I rarely use the CPU. So in this case, if the CPU bound applications arrive first, it occupies the CPU for a long time because the burst is longer, followed by a bunch of IO bound processes, right? Quick question. Then would you want to be under the scheduler where it just depends on who arrives first? Probably not, right? As you can see, it's so different in this case, right? The next also simple policy is what we call round robin. Round robin will do this. So I would split the CPU time into quantum, assuming, let's say I can split the time. Now I can preempt and pause the progress, right? Each process would take turn to run for this time quantum. And I have a timer interrupt that will count the time, how long has it passed. If it passed some threshold, that's a quantum, I switch to another process. So again, the same ABC scenario, and let's say the quantum is 2 seconds, right? Let's say a quantum is 2 seconds. What will happen is because A arrived first, A run for 2 seconds, then pause. A run for 2 seconds, then pause. B comes in, run for 2 seconds, then pause. Then C comes in, run for 2 seconds, then pause because of round robin. Then A comes in because you just do ABC, ABC, ABC. Everyone gets 2 seconds. So A run for 2 more seconds. Then B and C come in, only have 1 second left. So I just run 1 second, 1 second, and then back to A. Right? Benefit is usually this will give you better response time because everyone at some point will get the service eventually, pretty quickly actually, because we do round robin. The trade-off is, first of all, if queue is too big, if let's say queue is like 1 minute. If queue is 1 minute, it's just basically first come, first serve. Who arrive first get to go, and that's it. Too small means that every time you switch from A to B, B to C, C to A, context switching happen, that takes also a long time. So if you do queue that's too small, you have context switch overhead. That is why for systems that use round robin, you configure to like 10 to 100 milliseconds. Because if you remember the CPU burst graph that you saw earlier, most of them finish after 8 milliseconds. So this will take care of most scheduling. But if you have to have a really, really long process, it will prevent that process from occupying your CPU and starve everyone else. Now here's a turnaround time with different quantum lengths, as you can see, right? Quantum length of 1, 2, 3, 4, 5, 6, and 7. You have 4 processes running. The average turnaround time is, as you can see from this plot. Turnaround time again is how long do I have to take until I finish everything. And the quantum can make some impact. All right. So who can come up with a better scheduler? How many people see the when you go shopping, right? Have you saw that there's like a line for anyone that buy less than 10 items? Why do we have that? Why do we have that? Yeah, so for people who doesn't have a lot of job, right? Finish quickly and then go. So we call this shortage of first. So I'll leave with this slide because actually we are almost done with the majority of scheduling I want you to know. Shortage of first, follow that. I want to measure the length of the process until the next CPU burst. Not until. I want to measure the length of the process of my next CPU burst, and then I schedule the process that has the shortest time. So let's assume the same way you do then B, C, and A, right? Because you know that A takes the longest. I finish B and C first, then A. Benefit, this is optimal. This is optimal in terms of waiting time. That's why it works for those shopping lines. It's optimal for the waiting time. If I don't buy a lot, I don't have to wait in the long queue. Here's the problem. It means that I need to predict my how long do I have to run, right? Which is not always easy. If you run a program, even let's say you have if else, right? And in the if side, you have a big loop. In the else part, there's nothing. How often can you predict whether you're going to the if or the else? It depends on the dynamic information, right? So you have to be able to predict that. We will then talk about time estimation in the lecture on Thursday. So let me wrap up today. Basically, we left with shortage of first. Again, I'll compare this like the shopping line with the less than 10 items can go first kind of thing, right? That's it for today. Thank you so much. We'll see you guys on Thursday.